Let's get into setting up the Kalman filter. The basic problem is that we have a noisy observation of something and we want to estimate it. So in this case, if X is our signal and V is some sort of noise, our observation is Y. And we want to estimate X from Y. The problem is this is really hard to do. If I were to give you the number 40 and say that is composed of two numbers, what are they? You would have no idea where to start. So we have to assume some sort of knowledge about X and V. So in order to encapsulate this knowledge, we're going to re-express it, I guess, or rephrase the problem. We'll do this a couple times as we work toward the actual Kalman solution. So what if we knew, for example, that the signal came from some sort of autoregressive process? Autoregressive means that the signal at time n is equal to some function of the prior samples of the signal plus an input. So in this case, we could say, what if x of n is equal to x of n minus 1 plus some input w. We often assume that we really don't know much about w, and so we call it noise. I'm sure this is a bad habit that we get into in signal processing, but anytime we don't know a signal, we just call it noise. And to make life easier, we're going to assume that W is zero mean. We'll talk more about W later. Okay, so if we know that much, now we come along and we take our measurements. As indicated and discussed above, y of n is equal to x of n plus v of n. So now we have two noises. We're going to call this second noise our v of n that we started out with. We're going to call it our measurement noise. With this type of knowledge, we could do perhaps a little bit more. For example, if lambda was some number close to 1, we could assume that when we're trying to get y of n out, that values of y of n are going to be very closely related to each other. In other words, we could assume that x of n, which is essentially going to be the same for all time, plus the addition of this w, this noise sequence, we could say that the constant or relatively constant part of y would be associated with x, and anything that varies dramatically from sample to sample would be associated with v. We'd be a lot more specific than that when we worked out the math, but that would be the general idea. However, so this tells us something. Let's go ahead and generalize this once more, and we'll get now to what's actually going on with the Kalman filter. The first thing we're going to do in our generalization is assume that we now have not just single signal samples that we are trying to work with, but actually we have vectors. So we'll go back to our bolded variables are vectors, and in place of our x of n is equal to alpha x of n minus 1 plus wn, we now have a more general case where we have x of n is equal to a matrix A, and that matrix can maybe change with time, times x of n plus another matrix B times a vector of noise. And we're going to call this the state equation. The state is x. X of n tells us what things look like right now. The state of our system, the state of our signal, whatever you want to think of it as. The state equation explains how the state at time n is related to the state at time n minus 1. Now, in our previous example, we then made an observation of x that was corrupted by noise. In the Kalman filter, we're doing the same thing, except we're not reading x directly. We're actually reading some transformed version of x. So c in this case is a vector, and thus we're observing some vector times x plus some observation noise, and this is called the observation equation. So this is our basic notation for a Kalman filter. I think it might be good to go through a few examples to show how this works out. It's nothing like an example to make things clearer. So for this example, I have a GPS watch, and it does a pretty good job of tracking my motion, sometimes not. So the problem with GPS is that it is only accurate to around a radius of 30 feet. So if I'm walking or running and I get errors within 30 feet, that's quite a bit. It would jump around dramatically and maybe look like I was some sort of quantum particle leaping from place to place, covering a lot of ground very quickly. So we want to do something to kind of smooth this out. So our observation then would be what the GPS tells me my position is, and the state would be my actual position. Although I can move more than just a straight line, for now, just to make the setup easy, we're going to assume that I'm moving in a straight line. Okay, so our state vector we're going to have it be my position along this road, along this straight line, and I'll also put in speed. As I'm putting together this example, I realized that maybe using a bicycle example would be better, because in that case you're more likely to be moving in a straight line, and you're more likely to have a constant or near constant speed. So this will be our state vector x at time n. And the GPS is not going to be observing our speed, it's only going to be observing our position. So the observation is going to be y of n is equal to x of n plus noise. Okay, so let's define then our matrices associated with this. A, what is A going to be? A says that my position at time n is going to be my current position plus delta t times my speed. And we're going to assume that my speed stays the same. Well, of course it doesn't, but that's the point of having our W here. Okay, so then what B is our matrix multiplying W. What does it look like? This can be defined in several ways. In this particular way, we're going to assume W is a scalar and it's multiplied by 0, 1. In other words, there's no noise that's going to teleport me around, but it is possible for my speed to change. And so B will indicate then that there's noise on the speed. In other words, I can change the speed in some arbitrary way. And since it's arbitrary, we're going to call it noise. What about the observation vector? It's a matrix, but in this case, it will just be a vector. And it's going to be a row vector. So in this case, we're observing only the position and not the speed. So we'll get something like this. Now we can put this all together, and we can say that our position at time n and our speed at time n are defined by our A matrix times x at time n minus 1 and speed at time n minus 1. So in this case, the default assumption is maybe from conservation of momentum in physics that our speed is going to stay the same unless acted on, in this case, by W. And our observation, which is of our current position, that's going to be selected using our C matrix from x of n and s of n, and that there will be some noise with that observation. So this is how we might set up a problem for a Kalman filter. And you can imagine that if we were actually working in multiple dimensions, for example, not running in a straight line, but hiking, where we had 3 dimensions in which we could move, that this would get more complex, but that the idea would remain the same. We would have speed in 3 directions, x, y, and z, and also 3D position, x, y, and z. And our speed would relate to the position. If we're actually a moving object, such as, well, I guess people are moving objects, but if we were a car or a bicycle, we might assume that the speed remains the same and is only affected by the acceleration. And so then the process noise, the input, would not directly affect the speed, but rather the acceleration. And in that case, we would pretty soon have a 9-dimensional state vector with xyz position, xyz velocity, and xyz acceleration, with the noise acting on the acceleration. Our intermediate example of how to set up the Kalman filter idea introduced this idea of an autoregressive process. So I guess as our second KalmanSetup example, let's put an autoregressive process into the Kalman framework and see how that works. We will expand this out to make it a little bit more general, and essentially then x of n is going to be equal to a bunch of previous samples, all plus wk. So w is not then, that shouldn't be wk, it should be wn. W is not part of the sum. Okay, so this says that our current sample x is going to be equal to the A coefficients times P previous samples of X. In the case above, we had P would be equal to 1, and so we just had a single alpha, but now we have a bunch. So let's rewrite this in terms of state equations. So first we're going to need our state vector to include the P previous samples. Then we need to come up with a transition matrix. So our A is going to be such that x of n is going to be the sum of all the previous x's. So that will be an. We started our numbering with 1, an 2 up to an. Now it's possible that these a's could change between every sample, hence the subindex of n. But if this is constant, which is actually more frequent, then we wouldn't put that in there. So that tells us what x of n is going to be. It's going to be this linear combination of all the previous ones plus the noise, but we'll deal with that separately. Now we need to go through the process of changing or updating x. So our x vector being the most recent samples, we're going to come in and have something like this. Where this thing is going to be I of size p minus 1. And then the last column will be zeros. Finally, actually not finally, we have a couple things left to do. Our noise matrix B is going to be just 1 with a bunch of zeros, because the noise is only added to the current input sample. The rest is taken care of through our autoregressive update. Now we come to the finally. This is going to be 1, 0, 0, 0 times x. So we're pulling out just the most recent sample plus some noise. So spend a minute and double check, put on a piece of paper, write these equations out, and convince yourself that A is the correct matrix. We've already discussed how the first row is going to be multiplying the previous x vector, giving us the autoregressive update. And then the second value of our updated state vector, which is x, is going to be equal to 1 times, I'll just put it right here so we can visualize it. This is going to be x of n minus 1, n minus 2, so on and so forth, to n minus p. Yeah, that should be a little bit easier. So now we can see that x of n minus 1 now was at the top. It becomes the second position in the matrix, which is what we want right there, and so on and so forth. So that having this identity matrix is shifted down by 1 in A essentially shifts down all of these values by one sample.